We will now continue discussing the calculation of equilibrium concentrations from Kc using a new example. In the previous lecture, we first learned how to calculate equilibrium concentrations from initial concentrations and the value of Kc for an equilibrium reaction. In this and the following two lectures, we will practice on 3 additional example problems. In addition, we will see how to incorporate the reaction quotient, Qc, into this type of problem. As before, please be sure to pause these lectures regularly so that you can work the problem along with me. This will be the best method of developing the skills for solving this type of problem. Let's begin by reviewing the procedure. Note that we will be adding in a couple of steps to our procedure. First, once we have read the problem, we fill in as much of the ice table as we can. Recall that if a pure solid or liquid appears in the reaction, it takes no part in the Kc expression, and therefore we do not need to tabulate its values. Step 2 is now a little different. If either the reactants or products have an initial concentration of 0, then the reaction will proceed in the direction to form those species. We saw this in the previous example. Otherwise, we must use the value of Qc to determine the direction of reaction. Step 3, at that point we have to introduce a variable in place of how much each concentration changes. 4, we then determine what the equilibrium concentrations should be in terms of the initial concentrations and the variables. And finally, we substitute the algebraic terms into the equilibrium constant expression and solve. Please take a minute to pause this video and write down the steps in the procedure so that you can refer to them as we continue to work this problem. Here's our example. Barium fluoride is a sparingly soluble salt. This means that it does not dissolve very much at all in water. When added to water, it dissociates according to the equilibrium, BaF2 solid, forming barium 2+ ions in solution, plus 2 fluoride ions in solution. At 25 degrees Celsius, the Kc value for this reaction is 1.84 times 10 to the negative 7. If you add about 10 grams of solid barium fluoride to 100 milliliters of water, what are the equilibrium concentrations of the barium 2+ ion and the fluoride ion? As always, we begin by writing our Kc expression. In this case, the barium fluoride, because it is a pure solid, does not appear in the expression, and Kc is just equal to the concentration of the barium 2+ ion times the concentration of the fluoride ion squared. We begin by building our ice table for the reaction. As always, the top row contains our chemical equation. This is followed by the initial concentration row, the change in concentration row, and the equilibrium concentration row. Notice that because it does not take part in the equilibrium constant expression, we do not include any information about the barium fluoride solid. The initial concentrations of each of the ions are both assumed to be 0 initially. Since we're forming the ions, we know the changes in the products must be positive. We do not know the extent of reaction, so we use the variable x as before, and we make sure to multiply x by the stoichiometric coefficient for each product. This means that our change in barium ion is plus x, and our change in fluoride ion is plus 2x. Then we can finally express our equilibrium concentrations in terms of initial concentrations and the changes. As before, we just read down the column. For the barium ion, we begin with 0, we add x, and this results in an equilibrium concentration of x. For the fluoride ion, we begin with 0 molar, we add 2x, which results in an equilibrium concentration of 2x for the fluoride ion. And now we begin to look at the algebra. The first step is to substitute the equilibrium concentration row into our Kc expression. When we do this, we get x from the barium 2+ times 2x quantity squared for the fluoride ion. The algebra for this problem is fairly simple, but we still must be careful not to rush it. The first step is to substitute in the value of Kc, 1.84 times 10 to the negative 7. Notice that I have inverted the equation to make it easier to solve. At this point, we can square out our 2x, resulting in the value of 4x squared. We can then multiply the terms on the left-hand side, which yield 4x cubed equal to 1.84 times 10 to the negative 7. Now we can solve directly for x. First, we divide through by the 4. This gives us 1.84 times 10 to the negative 7 divided by 4. When we divide, we get 4.60 times 10 to the negative 8. And finally, since x is being cubed, we have to take the cube root of 4.60 times 10 to the negative 8 to finish solving for the problem. Many calculators have a dedicated cube root button, but if yours does not, there are several options you can use. Firstly, if you have the x to the box button, you can type in 4.60 times 10 to the negative 8, followed by x to the power, followed by parentheses, 1 divided by 3, close parentheses. Or if you have a caret button, or the little hat, you can type 4.60 times 10 to the negative 8, followed by the caret button, followed by parentheses, 1 divided by 3, close parentheses. Note, in both of these cases, we are using the fact that the cube root is equivalent to taking the 1/3 power. When we do this, we find that x is equal to 3.58 times 10 to the negative 3. We're now ready to calculate the equilibrium concentrations. We use the equilibrium row from our table to help us do this. First, we notice that the barium concentration at equilibrium is just equal to x, which is 2.58 times 10 to the negative 3 molar. For the fluoride ion, the equilibrium concentration is 2 times x, or 2 times 2.58 times 10 to the negative 3. This is equal to 7.17 times 10 to the negative 3 molar. We can now add these values to our equilibrium row in our table. As in the previous example, the last step is to check our answer. When we substitute the equilibrium concentrations into our Kc expression, we should return a value that is equal to or very close to the value of Kc. For the barium ion, we have 2.58 times 10 to the negative 3. And for the fluoride ion, we have 7.17 times 10 to the negative 3 squared. When we multiply these out, we return the value 1.84 times 10 to the negative 7, which is equal to our original Kc value. This concludes the second lecture in the series on calculating equilibrium concentrations from the value of Kc. In this lecture, we worked a second example which introduced several new concepts for chemical equilibrium calculations. First, when pure liquids and solids take part in an equilibrium reaction, we do not tabulate any information about their amounts in the ICE table. This is because they do not take part in the equilibrium calculation. Second, when we have zero amounts of either reactants or products, we do not need to use QC to predict the direction of the reaction. We react to form whatever we don't have. Third, even when the algebra seems simple, take your time to avoid mistakes. And fourth, always remember to check your work. We will look at 2 additional examples in the following 2 lectures. These will be a little more complicated and will involve using QC to predict the direction of reactions.